Okay, it's the appointed hour. So welcome everybody to today's webinar. And the topic is on systematic issues. So one of the reasons I've put this together is it's over the last, I suppose, couple of years really, the discussions I've had with end users has more and more moved towards a lack really of understanding of what systematic issues are and how important it is to be aware of what they are and obviously how systematic issues can have a very severe consequence on the safe operating of the plant. So as a result, I thought I'd put together a webinar just to go through it. The blog was released a few weeks ago, and in fact our CFSE, rather our FSE 100 class, which by the way I shall be teaching in England next week, coronavirus notwithstanding, we'll go into the differences between random and systematic issues and why systematic issues play such a significant role in or either the safe operating or the dangerous operation of the plant. However, before that, let me give a brief introduction of Exeter for those of you that are not familiar with Exeter. This is our 20th anniversary, official 20th anniversary year. The company was officially started in 2000. It was started by Dr. Bill Goebel and Rainer Fuller, and the reason they did that was because they recognized that companies or manufacturers were going to struggle to get to grips with what was then a new standard called IEC 61508, which was released in 2000, targeting manufacturers of safety-related equipment. Since then, of course, the company's grown exponentially. We no longer just do 1508 certification. We also do cybersecurity certification, and we do personnel certification. Again, some of you may be CFSEs or CFSPs, Certified Functional Safety Experts or Certified Functional Safety Professionals, and we've been running that certification program now for 15 years or more. We've also introduced Lifecycle services, so we provide full lifecycle services for functional safety, alarm management, and cybersecurity. And these three are very important because they all play a part in the overall safe operation of a plant. Coupled with that is the lifecycle tools that we have that support functional safety, alarm management, and cybersecurity. We've also expanded beyond just the original two locations, which were Germany and the USA, and we are now completely global. How we measure our success is that, again, a lot of people think we're the best kept secret because we actually have the largest market share in certification. So 2 out of every 3 devices has been certified by Exeter. We've also moved away from being just owned by the 2 founders because they realistically want the company to continue beyond their retirements, and therefore we now have more employee ownership. We've also got more than 100 experts now, probably closer to 120 global experts. We've done over 1,000 certification assessment projects, and with the Excellencia tool modeled more than 500,000 SIFs. Reference materials, I'm sure some of you have some of the books that we've written. We do provide a lot of free information. I mean, these webinars being one, of course, and they're recorded and they're available through the resources tab on the website, the exida.com website. We also have a number of white papers that are there too. The books that you see can be purchased through the website. And we also provide the SAEL, the Safe Automation Equipment List, which will give you manufacturers' devices that are certified for specific functions such as sensors, pressure transmitters, etc. I always encourage people to utilize the resources on the website because There's a lot of information there, and it's mostly free. The books, of course, you have to purchase, but if you, for example, the FSC 100 course, usually that for the open enrollment comes with the 3-book package, the safety book package, because the course is structured around the practical SIL target selection book you see here. We also have a SIS design book, and there's also a safety book, a study guide to help you in preparation for the CFSP or the CFSE exams. Now we have the equivalent cyber side of things. We have a cybersecurity book, Pragmatic Approach to Cybersecurity for 62443. We also have a study guide for cyber. So the equivalent of CFSE is the CACE, which is the Certified Automation Cybersecurity Expert. And then we have the CACS, which is the equivalent of the CFSP, which is a Certified Automation Cybersecurity Specialist. And therefore the study guide will help prepare for that. So there's a lot of information. Please make use of it. And also there's a full library of webinars on functional safety, either certification topics, cybersecurity, alarm management. Me, some of you may know me already. I've been around in industry for 43 years now. And I started life as a design engineer doing hardware and software development for a company called ICS in the UK, designing emergency shutdown and fire and gas systems and addressable alarm systems as well. I've then spent a number of years in the process world doing automation, and finally came back into safety about 8 years ago with Exeter. I'm one of the leading instructors for the functional safety, the FSC 100, and I also teach the cybersecurity courses as well. Okay, with the introductions done, let's get to the meat of today's webinar. So why bother with systematic issues? So systematic issues, a lot of people say to me, what are actually systematic issues? And most often on times, people will say, well, that's the human factor. Well, that's partly true. Those of you that have heard some of my webinars before and have been on our training course know that I always refer to it as the 3 Ps. So from a safety instrumented system design point of view, we can help prevent the introduction of systematic issues by addressing the 3 Ps, and those are that we make sure our people are properly trained and competent to carry out the life cycle tasks they've been assigned, that we do have properly documented procedures that are easy to understand and that are being followed. There's been numerous instances where accidents have occurred because either the startup procedures were violated or they weren't being followed, or there was some shortcuts taken during maintenance and not, again, adhering to the procedures. And then the 3rd P is the paperwork, having the paper trail, making sure that we can prove we're doing what we said we were going to do. So this would be doing audits and making sure that proof testing is being done properly, mechanical integrity is being done properly, the procedures are being followed, etc. Another issue is not understanding the application or the environment. And these pictures that I'm showing here, there was a very amusing, it was a video some time back showing that a car had gone into the bay. So they'd sent a truck to lift it out of the bay. Well, of course, the truck wasn't suitably big enough, so that fell in. So they got another one, the green one that you see here. And of course, this one wasn't suitable for the load or the application, and this one also fell in. It was like a comedy of errors. So this is, again, not understanding application or environment or capabilities of the equipment. The other thing is not being easy to measure. Systematic issues are not necessarily easy to measure. With failures, with faults, with equipment faults, those are relatively easy to see and measure. But systematic they're insidious. They can only be eliminated by a change in the design specification, for example, the design itself. So again, if the designers don't fully understand the operating conditions and the environment. So for example, if you're designing a system to handle a refinery, and that refinery is going to be located in Alaska, and you don't design with heat tracing in mind, then you're going to have a problem with freezing pipes. So it's important that the designers understand the environment. And then the other factors are these 3 Ps, of course. And the IEC 61511 does emphasize the need to be able to manage systematic issues, which of course means having a proper functional safety management program in place to manage those particular issues. It also means we have to follow what's known as Reger Gap, recognized and generally good accepted engineering practice. And in the UK, it's COMA, and the US, of course, OSHA CFR 1910 requires operators of hazardous processes to follow Reger Gap. And of course, IEC 61511 and now what was the old ISA 84, which is now ISA 61511, those are recognized as being Reger Gap. 1511 is built around the safety life cycle. So effectively, there are 3 stages. There's an analysis stage where we have to assess and analyze where our risks are according to our hazards and what the consequences of those hazards are, and therefore what we need to do in terms of defense mechanisms to be able to reduce those hazards to an acceptable level. Then, of course, we have to design to meet that. And we have to be able to verify and validate our design. And then we go into operation and maintenance. And some of you probably heard me say this many times before, the old 20-20-20 adage, 20 weeks in design, 20 months in implementation, and 20 years in operation. So again, if we don't follow the requirements during operation and maintenance for proper testing, proper maintenance, replacement of devices or refurbishment of devices as they get to the end of useful life, then we're very quickly going to have a SIS and SIFs that will deteriorate and will not be providing the level of protection that we need. So the purpose of 1511 is to help us follow a life cycle, gives us consistent methodology so we can achieve optimum results by balancing the design to meet the risk requirements, and gives us a means to consistently measure performance. The other thing, of course, is that 1511 is a performance-based standard. So it's not prescriptive. It will say this is what you need to do, but it doesn't tell you how to do it. However, you are expected to be able to measure your performance. So it's important that we have the right indicators to be able to measure performance. And the objectives, of course, here is we're trying to avoid these systematic errors and systematic faults creeping in, and we're also trying to manage and reduce the potential for random faults that could cause equipment failures. In either case, we're looking at providing a consistent and global framework that we can use to make sure we have repeatable designs that are not overly engineered, or worst case, under-engineered, so they're much, much worse and potentially more dangerous. The over-engineering would be more expensive, of course. So we want to balance it. If we do it right, it actually saves us money and ensures that we have a consistent methodology. Now, this is a very much used pie chart. You've probably seen this multiple times before at different conferences, but the Health and Safety Executive in the UK did a study in 1995, which they repeated in 2003, looking at the causes of accidents involving control systems. And what they discovered was, in 95, that 44% were due to bad specification. And of course, following that, design and implementation. So of course, if our specification's bad to start with, the rest of it's not going to be much better. But more importantly as well, if you look at the back end, there's 35% in combination from operation and maintenance and changes after commissioning. And these were all typically systematic issues. So they did this again in 2003, and the sad part about it was that they didn't really notice a huge difference in the 8 years, because people still do not see the benefit of trying to manage and prevent systematic issues from creeping in. The dear late Trevor Kletz used to say, if you think safety is expensive, try an accident, because accidents are going to cost significant amounts of money and possibly lives. So systematic issues are the number one cause of accidents. And this is why we have to make certain that we safeguard as much as possible from introducing these systematic issues. So this is an important thing to understand. So again, if we look at the life cycle, as I've said, the 3 phases, we have the analysis, we have design and implementation, and we have operation. And of course, we can do all of this front-end work perfectly. But if we neglect to do the right things in terms of managing functional safety, managing, especially when we get into the operation and maintenance phase, we could end up introducing potential systematic issues. So in other words, if we haven't done our front-end work correctly, if we haven't correctly identified the hazards, if we haven't done a layer of protection analysis to look at our worst case consequences, then we may not have sufficient safeguards in place to be able to reduce the risk to an acceptable level. And that's what it's all about. So I like to refer to functional safety management as the glue that holds it all together. And therefore, we need to make sure we're doing our functional safety assessments, and the standard identifies that there are 5 that need to be done. The first one should be done at the end of the analysis phase when we've come up with our conceptual SRS to make sure that we've covered everything correctly and we haven't missed anything in the PHA or in the LOPA. The second one should be done after we've done the design, usually during FAT or just after FAT, before it goes to site for installation and commissioning. And of course, the third one has to be done before we start up. So in the old 2003 standard, the FSA 3 was the only mandatory one. Now in the 2016, the language is such that if 3 is the first one you do, then you have to make sure you cover 1 and 2. So it really means that you should do 1 and 2, because again, the further down the life cycle you go, the more expensive it becomes to fix problems if you find them. And when you get to here to do the FSA 3, if you fail the FSA 3, then it can be quite costly because it will delay startup. Or if the end user chooses to start up, then they're assuming a higher level of risk. And the other thing you need to do is make sure you check with your insurance company if you're not self-insured to see that you're covered if you haven't passed an FSA 3 and you choose to start up. And then again, during normal operation, we have to now do an FSA 4. So the standard says this is a periodic assessment. Periodic, you can define what that period is. You might use the 5-year window between PHA revalidations to gather enough data to be able to do a reasonable review, assuming you've not had any incidents. And then again, if you do any changes, that's an FSA 5. So functional safety management governs the entire safety life cycle. And it's been beefed up in the 2016 edition now. There are a lot more shalls in there than there were before, and now you are required to allocate life cycle responsibilities. So roles and responsibilities have to be clearly defined. We need to have the proper procedures in place, and we need to make sure our people are competent. there's also a requirement now for, again, the word periodic reviews and assessments of the personnel working on any SIS. And the purpose, of course, of all of this is to help us manage the risk of systematic faults, so we don't introduce any problems. So how do these occur? I mentioned this already. You can have poorly specified or poorly done specifications in that they haven't been properly reviewed. They don't fully understand the operating environment, or it's been poorly reviewed, or the specification wasn't very well written and wasn't clear. Certainly with software, at least with hardware, there are things that we can see. With software, this is completely covert. In other words, faults, problems, bugs are usually covert. They're hidden, and the only way to find them is either through testing, and again, you can't possibly test all the permutations of software rather. So usually you find out you've got a software bug when the program executes a certain branch, and now something's not working. So software specifications need to be properly reviewed and specified. The instrument design itself, again, if it's not, so if you don't understand that you've got a harsh environment in terms of what's flowing through the pipes, so the valves need to have a certain material used because it's highly corrosive what's going through the pipe, and we don't use the correct or specify the correct valves with the right materials, then guess what? The valves are going to deteriorate pretty rapidly. So we need to make sure that we specify our equipment properly, and as the application software as well. If that's poorly specified or poorly designed and there are errors, or the testing isn't fully complete. So these can all lead to potential systematic issues. And of course, the problem with that is you could end up with failures on demand. And that's what we do not want to happen for a safety instrumented system and its SIFs. I see some questions are popping up. What I'm going to do is I'm going to address all the questions at the end, if you bear with me, get through the main presentation, and then I'll address the questions. So from the SIF design point of view, we have, after our analysis phase, and we've done our FSA1, we have to look at selecting technology. So 1511 is very clear about how we do that. You have two choices. You can either use 1508 certified devices that have come from an accredited certification body, or you have to do prior use justification, which means that you have to have sufficient failure rate data on the equipment that's being used in a similar environment and application, and it has to be pretty accurate. Because if not, then it's going to be very difficult to justify it. Then we do our architectural design, and then we define how we're going to test our SIF, whether it's online, offline, how we're going to do it. And then finally, we do our SIL verification. Now, the SIL verification is where we look to see if the SIF meets three barriers. The three are the PFD average or the PFH, depending on whether it's a low demand or a high demand or continuous, the architectural constraints, and the systematic capability. So when you have a SIL certified device, part of the process of doing the SIL certification is to go through and look at how was the device specified, how was it designed, were the people that were designing it competent and trained, what was the manufacturing process, what testing was done, what are the field failure records if it's a previous version. So all of that is analyzed during the during the certification, the product certification. So there's a confidence level, and that's why when you look at a certificate, it'll say it has a systematic capability of SIL 2 or SIL 3 or SIL 1 or whatever it is. If you haven't got certified devices, then the only way we can do that is through a prior use justification. which is an indication that the design is acceptable for the application. Then we would have to do our detailed hardware and software design with our safety requirements specification, and then equipment acceptance test. And we should also at this point now do a cybersecurity assessment, because again, cybersecurity is very important. Anything that is compromised from a cyber point of view, that is a systematic issue, and that can be the mother of all common cause. Because if you get compromised and you don't know you've been compromised, if the SIS is disabled, so it SIFs, even if the SIFs see a demand, they cannot operate correctly, that's going to have significant consequences, because the SIS and its SIFs are our automatic backup if the BPCS isn't able to contain the problem. So again, why is it important we do this? Well, if you just look at the accidents that have occurred, Deepwater Horizon, there were 11 fatalities, massive environmental cleanup. The estimated cost from BP is greater than 60 billion. And there were systematic issues involved with that. The DuPont, the port facility, there were 4 fatalities. There were 3 million in fines for EPA violations. AB Specialty Silicones, again, 4 fatalities, 1.6 million in OSHA fines. Philadelphia Energy Services explosions, no fatality, but the plant closed with greater than 1,000 workers being laid off, and that was because they hadn't inspected piping. Aghorn Energy, 2 fatalities due to chemical release, and KMCO chemical facility, 1 fatality, 2 seriously injured due to fire and explosion. In most cases, there will be some form of systematic issue that's caused the problem, whether it's because the procedure wasn't followed, whether it's because mechanical integrity wasn't done properly, testing wasn't done properly, maintenance wasn't done properly. These things all contribute. And there's the quote from dear old Trevor: if you think safety is expensive, then try an accident. So it's very important to be mindful when it comes to systematic. How can we avoid systematic issues? Well, we make sure that the SIS and its SIFs have been designed using certified devices wherever possible. Now, I know that's not necessarily the situation, because some legacy sites will have existing equipment. So we have to make sure that we have enough justification for the existing equipment. We have to make sure all our personnel associated with the SIS are properly trained and competent. And it has to cover design, implementation, operation, and maintenance. This is also true of any contractors or third parties you're using. So if you subcontract the SIS design to an engineering company, the standard now requires that they also have a functional safety management system that they can demonstrate is in operation. They have properly competent and trained people, and they have roles and responsibilities defined. If not, then they won't meet the requirements of 1511. We should do our periodic assessments of all our SIS personnel. So again, end users need to define what that period is, and this also applies to engineering companies. Engineering companies fall under the category of end user. So if you're an integrator, if you're an engineering company, you fall under the end user category. We also need to make sure that all our procedures are complete and concise, so they're not open to misinterpretation wherever possible, and more importantly, they're being followed. And I'm a great exponent of the checklist. I always use the pilot analogy. A commercial pilot may have flown thousands of hours, but every time he gets into the cockpit, he refers to his pre-flight safety checklist. So this way, if you have a checklist, you won't miss anything. Now you see this guy on the right, you think he's properly competent and trained? So how can we avoid systematic issues? We can ensure that the paper trail is there recording all the specifications, verification and validation activities. We have all the test results, all the training and competency logs are recorded, We make sure our functional safety management plan is in place and being followed. And we ensure that all the contractors and suppliers that we're using are properly qualified, competent, and also have the correct FSMP in place. We should be conducting functional safety assessments and functional safety audits. Another topic that I will be dealing with in the next month or so will be the need for doing FSA 4 and why we should do that. Because again, if we're not measuring our performance, how do we know that our design is meeting requirement? So we should be using some KPIs, some key performance indicators. And I've mentioned this before in previous webinars. You could use leading and lagging indicators. And I did a webinar on this 18 months to 2 years ago, which is recorded, so you can always go and have a look at that. There's also a paper I wrote on this that's on the website. So leading and lagging is one method that you could use to help. And that's where you look at what events have we had, even near misses, what failures have we had, what violations in policy we've had, any problems with systematic issues, and then we should be looking at reducing those and correcting those. And of course, then the leading ones are looking at the possibility of a future event. So are we doing our proof testing on time properly? Are we doing our regular assessments of our operation and maintenance people? Are we doing all the things that we should be doing from a mechanical integrity point of view? Are we replacing and refurbishing devices at the end of the useful life, and so forth? If we do an audit, what we need to make sure is that any non-conformances or discrepancies are followed up and addressed within a given time frame. And again, this would have to be defined by the end user. And it's important to make sure that we do implement any recommendations coming from the functional safety assessments and audits. So again, the 1511 says that we need to make sure, again, if FSA 3 is the first one we've done, we have to make sure 1 and 2 are covered, or if 1 and 2 were done, that any recommendations that came out of those have already been addressed. So it's important to make sure we do that. So why bother with systematic issues? Again, we need to make sure we have a proper functional safety management plan in place. We need to make sure that our suppliers also have competent people and have FSMP in place. We can use tools and checklists to help consistency and repeatability. We need to make sure that we have our roles and responsibilities defined, and therefore we have competent and well-trained people that are involved in the process and the life cycle. You can use independent qualified third parties to conduct FSAs and audits. That means that you've got you can show independence and of course non-bias. But again, they have to be qualified. And make sure you address any discrepancies or non-conformances from the audits in a timely fashion. Be vigilant in following procedures. So again, with operations and maintenance people, if they're not following procedures, then we need to understand why. Do they not believe that the procedure is correct? Do they think there's a better way of doing it? So if there are improvements that can be made to the procedures, then they should be implemented. And make sure that we have roles and responsibilities defined. It's no good just having an organization chart with Fred up there as being responsible if Fred doesn't know what he's supposed to do and what his responsibilities are. That's not going to work. Okay, just some information about upcoming courses. We have, as you can see here, quite a few courses planned in different parts of the region in the US. And these are available through the website if you're interested in any of these. And we also have online self-paced training courses available as well. So here again, if you can't make an open enrollment, this is another way you could go. Okay, with that being said, thank you. And let's see what questions that we had. Okay. Anyone got any more questions? Okay, there's a question here. Excuse me. Just anyone have any questions? Feel free. Okay, let's see what we've got here. I've always worked in oil and gas operations, and my main concern is the software quality control in SIS. Yes, I can believe that. Though SIS PLCs use LVL, which is limited variability language, and there is a general misconception that it is safe and reliable not to a proper quality control system, and just having a FAT followed by SAT are good enough. I've witnessed software errors numerous times and limitation of FAT SAT. Yeah, this is quite interesting. Again, usually with the logic solvers, as part of the logic solver certification, depending on who's done it, the function blocks that are defined, the programming is looked at very carefully. When it comes to implementing and doing the design using the tools and the blocks that the logic solver supplier gives you, you need to make sure again that and this comes down to roles, responsibilities, and competencies, that whoever's writing the test plan knows what they're doing, and make sure that the tests are written properly. Again, when we teach the FSC 100, we encourage people to use a modular approach for the software, for the application software, not to make it too large, to make it fairly easy to construct, to design, and to test. And I agree with you here. I've seen it too. I used to go offshore years ago, and I could tell you some horror stories that I saw. Is this something on Exeter's radar? Well, this is part of, it's a good question. We get involved for doing witness testing during an FAT as part of the FSA 3, for example. Oh, sorry, the FSA 2. We don't get involved in the design. We can certainly review what comes out in terms of the results, but it might be something that we could look at. We do, of course, from the certification side, we dig in a lot deeper, but you're talking about application here, which is different. But that's a good question. And as I said, I agree with you. I've seen it myself. I think that's why the standard has changed and put much more emphasis again on competency, because people say to me all the time, well, it's just written, the standard's written by a bunch of academics. Well, no, it's not. The 1511 committee is mostly end users, and they're the ones that are seeing this problem, which is why they have tried to tighten up the requirements around competency. Anybody else with a question? I don't see any more. Oh, there's another one, sorry. As an independent consultant doing SIL classification, how can we help in reducing systematic failures? Well, again, I'm assuming that you're certified and you've got the relevant qualifications here. So SIL classification. This should come out of the LOPA. So if the LOPA's done correctly, and oftentimes when we come in to do reviews, we find there's all sorts of problems with LOPAs. Primarily, what gets violated is the independence. Now, and what people don't realize is that, for example, alarms from the BPCS, they give a credit for the BPCS, they give a credit for the alarm. Well, that's not true, because the alarm isn't independent of the BPCS. So it can't be 2 credits, it can only be 1. How we reduce systematic failures, again, is to make sure that the functional safety assessment is done, and looking at how the design is done too. Anybody else? Can humans do random errors? Absolutely they can. Because, for example, you could have somebody, an instrument tech who's properly trained, who is following a procedure for recalibrating a trip point, but he's had a bad day. Maybe he hasn't had enough coffee. Maybe he had a row with his other half before coming out. Maybe his mind's on the football game or whatever, and he makes a mistake in the calibration. That is not a systematic error because he's properly trained. He's following the procedure. He's just not focused. That's a random error. It's not systematic. Well, thank you for that. There's a comment, great webinar, thanks. Does the life cycle methods vary in methods or rigor with the level of SIL that is to be met? Well, the requirements are laid out for the rigor on SIL. So of course, if you've got the process is the same. So if we've got a SIL 1 or a SIL 3, we still have to go through and do the equipment selection. And here again with SIL 3, it's very the standard gives some guidance. We have a lot more guidance on proven in use. And again, we go through this in some detail on the FSC 100 course. So we explain what you need to do for proven in use justification for a SIL 3, which is very tough. So yes, there are, if you don't use certified devices, then yes, you're going to find that's going to be a very tough one to meet the SIL 3 requirements. And of course, the proof testing is going to be certainly with the interval. So you're not going to get away with a 4-year proof test interval and a 30-year mission time. That won't fly. So there will be restrictions on what you can and can't do. How to find what is the minimum that has to be maintained? Well, another thing I say when I teach the course, and I use this tongue-in-cheek, I say RTFM, read the flaming manual. You need the safety manual, because if you're using Excellencia does it all for you because it has all the information in the database. But if you're not using Excellencia, then you must have the safety manuals. And it's a good thing to have the safety manuals anyway, because the safety manual includes information regarding useful life. So again, you need to know when the device has to be refurbished and replaced, because that should be included in your mechanical integrity and you should be tracking it. Also, the safety manual will include a recommended proof test. The manufacturer will give you a recommended proof test to achieve a certain coverage factor. So again, if you're not using Excellencia, you would need that information to be able to know what proof test you need to do to achieve a certain coverage. Now, the proof test interval is normally a function of end user practices. So the end user may say, well, we're not going to entertain anything less than 2 years for proof test interval. And then you have to look at mission time. There's a whole nother webinar I did on the relationship between the proof test interval, proof test coverage, and mission time, because there's no such thing as 100% proof test coverage. And if you think there is, then you're fooling yourself, because there isn't. You'll never get 100% on a valve, so don't even start with that. So this safety manual will tell you when you have to replace and refurbish. The proof test interval is usually a function of end user practices. That's why you shouldn't design in isolation. I had one client where the engineering company, in order to meet the SIL target for the SIF, used 3 months proof test interval. And of course, the end user said, well, that's impossible. We can't do 3 months. So they were already set up to fail. So that's why it's important to make sure you understand the practices of the end user, the site, talk to the maintenance people, find out what their sore thumbs are. Don't put in proof test intervals that are not realistic and will never be achieved. As a way of example, would a covert trace heating failure, no low temperature alarm installed, constitute a random or a systematic failure? Well, that's an interesting one. Depends how, if it's been poorly designed, then yes, it could be a systematic, because if there's no alarm, then that's a design issue. Because then if the heat tracing fails and you don't know it's failed, then it's a potential systematic. Okay, anything else? How do you define competent at both engineer and technician level? It's an area that's often grey in my experience, and simply having a qualification doesn't. Yeah, you're absolutely right. I have always said, and I've had some arguments with people on this, that competency is a blend of experience, knowledge, and capability. So of course you need a certain level of technical understanding. So for example, if you're maintaining a SIS with its SIFs, you need to know which each SIF is protected, what's it protecting against. You need to know how the equipment in the SIF operates, and of course you need to know how to test it. So these are fundamental things you need to have. But also, if you're young, and this is one of the problems, of course, that you may have technical competence and ability, but you won't have necessarily the experience. And a lot of the old hands will be able to look at a situation and know immediately what to do. So I've always said it's a blend of knowledge, experience, and capability. And that's why, again, the standard has in there that the assessments need to be done periodically. It doesn't say how you do those assessments, but you would need to do those. How exactly do you define systematic issues? Well, I did mention that. I said it's the 3 Ps. It's, people, are they competent and qualified to do the life cycle task assigned? Procedures, are they well written, easy to understand and being followed? And of course, paperwork, do we have a paper trail that generates, shows that we're following that? Okay, that's some good questions. Thank you for that. If there are no more questions, I can end the session. If you think of anything else, then please feel free to email me. The email address is below. I'm always happy to answer any questions afterwards. And of course, if there's anything we can help you with, any courses or any support, FSAs, etc., please feel free to contact us. So that just remains me to say thank you all. Enjoy the rest of your day, wherever you are, and look forward to you attending a session in the future. Thanks very much.